Morning, Year 11. What a great start. Anyway, this video is going to be about intermolecular forces. Carrying on from, what is it, chapter 6. So what we've done so far is that we've looked at the molecular shape using Vesper theory, and then we've used our knowledge of polar bonds to then assign through the molecular shape if a molecule itself is polar or not. And that will help us govern what attractive forces there exist between two molecules. It depends on their shape, it depends on their polarity. Okay, so the syllabus point, yellow in the top corner there, it's a fairly large one, and we'll come back to it throughout the rest of this chapter. So we need to explore the similarities and differences between the nature of intermolecular and, oh, they're both inter. I need to change that. This is a good option. I always laugh because I never find mistakes until I'm recording something. So the nature of intramolecular and intermolecular bonds. Intra, within, inter, between. So the bonds intra are stuff like covalent, ionic, metallic, and inter we're going to look at now. And their strength and forces associated with each. And later on in the chapter, we're going to explain the physical properties of elements and compounds through these forces too. So intermolecular forces are attractions and repulsions too, I should add in. But the main thing we talk about is attractions between two adjacent molecules, atoms, or ions. Okay, they're all forms of electrostatic attraction or repulsion. Just like everything in chemistry nearly. But here we're not sharing electrons or transferring electrons like intramolecular bonds, okay? These are not about transfer of electrons or sharing electrons. These are just using the model of little magnets. So it all comes down to an unequal distribution of electrons in a molecule or not, and how areas with a lot of electrons, our little partial negatives or delta negatives, will be attracted to areas with less electrons, or our partial positives, our delta positives. So the mental model, so a little model that you got in your head, a 3D model of these little magnets. So some parts repel, some parts of attract, and they all kind of line up and attract each other in a certain shape and way. And it's a really good mental model to use. I still use it to this day. Really good mental model. Okay, so intermolecular forces are important in determining the physical properties of covalent molecular substances and a few others, particularly their melting and boiling points. Okay, and so it determines whether at our standard temperature and pressure, so I think that's 25 degrees, 100 kilopascals, basically everyday life temperature and pressure, whether they're solids, liquids, or gases. Okay, so there's three main types of these intermolecular forces, and we're going to go in a little bit more in depth, so a little bit of a depth study into a couple more that are related. But three main. They're called dipole-dipole forces, dispersion forces, and ion dipole forces. Okay, a little diagram on the right, but we're going to look at each in depth. Okay, there's this diagram here that I really love and really bring up. It arranges all the attractions that we're talking about in chemistry in order of strength. So up the top of the table, under the title, we've got our intramolecular forces. We've got our strongest ionic, so it's a cation to anion attraction. And look at that energy column. We haven't learned what the unit mole is, but we can compare these numbers. These numbers are telling you the force that you need to break these apart. Sorry, I shouldn't say force, the energy required to break these apart. So more energy, more force. I wasn't too far off the mark. So ionic bonding can take from 400 to 4,000 of these kilojoules to break them apart. So an awful lot. Big range there, but definitely at the top of the range. Covalent is weaker, Look at those numbers there, and slightly weaker, but in the same range as metallic. Have a look at the intermolecular forces though. We've got a few listed there, but that's okay. But you can see that the top number there is 600 and the bottom number is 0.05. So these are much, much weaker attractions because it takes less energy to move them apart. So we're talking about much, much weaker energies when we're talking about intermolecular attractions than those ones holding molecules together like ionic and covalent metallic. So that's your first message. They're much weaker, okay? And there's a range of weaknesses too in them. So let's take a look at our strongest one up the top there in the intermolecular, the ion dipole attraction. So our strongest intermolecular attraction. So ion dipole forces consider the attraction and repulsion between an ion and a polar molecule. Ion dipole, dipole, molecular dipole. So we're looking for an ion and a dipole being attracted. Okay, an ion has a permanent charge. A polar molecule or dipole has a partial charge. Okay, so a more positive end and a more negative end for that polar molecule. So a positively charged ion will attract to the more negative end of a dipole. So like the diagram on the left, so all the negatives are facing inwards towards that positive permanent ion charge, and the opposite, a negatively charged ion will have an attraction to the more positive ends of a dipole or a polar molecule and repulsion towards its negative end. So that's the diagram on the right. We've got a negative in the middle, and you can see there's 4 surrounding polar molecules, and the positives are all facing the negative, and the negatives are facing away because they're repelled. Okay, so as I was just saying before, ion dipole forces are the strongest of all intermolecular forces, and this is due to the amount of charge that's involved. Okay, the more charge, the more attraction. Okay, so when we've got a definite permanent charge like in an ion, that's a lot stronger than those partial charges in a polar molecule. So when we're involving an ion, it's much stronger because there's more charge there. Okay, so in the example here, for an example, an ion of a charge -1 also has more attraction to a positive than a blah, 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 blah. Okay, what I'm trying to say is, imagine if your ion has a single negative charge, like on the one diagram on the right there. It's going to be fairly attracted to those polar molecules. But if you have a 2- charged ion, it's going to be a stronger attraction there. More charge, more attraction, okay? So here's some more diagrams, and these ones are examples of some of the most common ion dipole interactions we have, because water is very common on Earth. So the diagram at the top is water's dipole molecules bent. Our positive end is our hydrogen end, and our partial positive, and our partial negative is our oxygen end. And look how they surround the chloride on the left. So we've got the chloride negative in the middle, and it's lined up and attracted to those delta positives of the water. So all the hydrogens are facing inwards. And on the right hand side, we've got our sodium, our cation. So it's lined up and attracted to the partial negatives of all the waters. So the red ends, the oxygen ends, are all lined up there, and you can see the delta negatives too. Okay, and the little animation you've got below is also sodium plus. See how they align and they're attracted to it. I like that little GIF. I think that explains that slide really well. So one of the most common examples of ion dipole is our ions dissolved in water, like sodium chloride dissolved in water. Okay, 2 videos for you to watch, a little bit more in depth, some examples from some good communicators. All right, that pretty much sums up ion dipole. Let's look at dipole forces. So ion dipole forces exist between an ion and a dipole. Dipole forces exist between a dipole and a dipole. So 2 polar molecules attracting each other. Excuse me. Since there are partial positives and partial negatives reasons to polar molecules, the partial positive of one molecule will attract to a partial negative of a nearby molecule, and also the opposite way around. So this causes polar molecules that are close to each other to kind of self-assemble into an ongoing pattern with attractive forces between the adjacent partial positives and negatives. Okay, so down here I've got a little animation. I put a lot of work into it. But you can see even before I've started that there's attraction between the partial positive and the partial negative of my model up the top. And then I've got an actual example of hydrogen chloride down the bottom there. And there's attraction between the chloride of one and the hydrogen of another because the chloride hogs all the electrons. So the chloride on one is a partial negative and the partial positive on another will attract each other. And let's see what they do. They attract each other and become closer. Oh, why did that skip? Let's go back. Let's watch that again. So much work went into that. Anyway, so when you get a large group of polar molecules together, they kind of self-align where they're maximizing the attractive force, but also there's a repulsive force between like charges too. And it's about a balance between them, okay? And that balance, that alignment is a way to reduce potential energy, okay? So it's the lowest energy possible where the opposite charges are closest and the like charges are furthest away. Okay, remember nature is lazy. So this diagram here, you've got your green arrows are your attraction and your grey arrows are repulsion. And you get this kind of order to the molecules. They all line up like little magnets. All right. This is a really good resource that I found and I added to these notes by the Concord Consortium. They're little interactive things that you can do, and I might show you here. So I've just put links in the notes. This one's on dipole of differing strengths. So click and it'll open. So explore the different attractive forces between molecules of varying polarity. What you need to do is select a pair of molecules. Let's do low polarity. And what you need to do is click and drag on this star and it gives you a relative force of how much you need to pull apart. All right, let's do it again. You can also hit reset. So you pull it out to about here and it overcomes those attractive forces between the positives and negatives there. Okay, let's contrast that with a medium polarity. Okay, notice the medium polarity has more positives and negatives in the molecule. Before there was 2 in the middle, now there's 4. Okay, click and drag. You can see this attractive force is much larger there, and they're animating it there with the, see those dashed lines? I'm pulling it out, and finally out of this distance it comes away. All right, now let's jump it up to high polarity. Look, now there's positives and negatives all the way around. So we've got more charges lining up. It should take more energy or more force to pull it apart. Well, I'm all the way out here. And then it finally does. So the more polarity you have in the molecules, the more attractive they'll be towards each other. Low polarity, a little bit of attractiveness. High polarity, a lot of attractiveness. You know what I mean. Okay, let's go back to our slides. So dipole of differing strengths. Okay, there's a wide range of strengths in dipole. I'm just going to zip back and let's take a look at this one. Let's find dipole on the intermolecular one there. And there we go. It's the third one down. 5 to 25. That's an awful broad range, okay? Let's look at the range even more. Oh, my little animation. Okay, here's where we were. Okay, the strength of dipole attraction and repulsion increases the stronger the dipole moment, or the more polar it is. The more polar the molecule, the stronger the attraction. So there's a spectrum, that 5 to 25 kilojoules per mole of strength of these. Now, up the top end, where you get really, really polar molecules attracting really, really polar molecules, so 2 of them, Unfortunately, and you'll hear why, chemists have given this another name, even though it's just really, really, really strong dipole attraction. And they've called it an unfortunate name as well. And they've called it hydrogen bonding. Now, there's a problem with that. There's huge problems with that name, okay? And I'll rant on about that in a second. So, for these molecules to be very polar, we notice that it's always within a molecule a hydrogen that's covalently bonded to a very electronegative atom. So a very electropositive atom like hydrogen bonded covalently to a very electronegative atom like oxygen, like we've got in water, and also nitrogen and fluorine. When you have a molecule with hydrogen bonded to oxygen, nitrogen, or fluorine, it makes it very, very polar. And water's a really good example because you've got that bent shape. It's very small. You've got two very polar bonds. You've got a very, very strong dipole moment with water. Okay? And because it's very, very polar, it attracts another molecule of water an awful lot. Two very polar molecules, high attraction. And so some chemists came along and said, why don't we give another name to that? Why can't we just call it very, very strong dipole-dipole? And their choice of name, hydrogen bonding, causes a lot of confusion. Okay? So here's a little bit more, some diagrams on the right, but I want to talk about the confusion in this name. Okay, when we're talking about hydrogen bonding, we're talking about intermolecular forces or intermolecular attraction. And the word bond I try to reserve for intramolecular attraction, covalent, ionic, metallic. Most chemists do too. The word bond we try to keep within that. Okay, it makes it nice and clear. Suddenly we're applying it to intramolecular attraction and it causes so much confusion. Okay, the hydrogen bond between molecules isn't a sharing of electrons at all. Okay, it's not like a covalent bond at all. It's just an attraction between two polar molecules that's really strong. Okay, it is an intermolecular force or intermolecular attraction. Okay, the criteria for it happening though is you need to look at the covalent bonds within the both of the molecules and determine whether they're very, very polar or not. Okay, try not to get confused. It can be a very confusing name. Okay, it's just really, really, really strong dipole-dipole attraction. Okay, so one way I try to remember those conditions within a molecule that can then give two molecules a really, really strong attraction is this little mnemonic. Because I hate the name, I've ranted on about that enough. It's down the bottom there. I've had N off of this terrible hydrogen bonding name. N off instead of enough tells me NOF, nitrogen, oxygen, fluorine. So I've had enough of this terrible name. So be careful with hydrogen bonding. It's not a covalent bond within a molecule. We're talking about two molecules attracting each other really strongly. But let's try to reserve the name bond for those intramolecular attractions like covalent, metallic, ionic. Horrible name. If only we could rechange it. Anyway, a little interactive on hydrogen bonding. Let's click on it, open it up. Okay, so we've got little water molecules here. They're bent hydrogens. Usually hydrogens in models are represented by little white spheres. Oxygens tend to be red, so there's a little shorthand there. So what we can do here is we can show the hydrogen bonding between molecules. We can show the partial charge. Oh, I like that. So remember, they're not ions, but these are delta positives and delta negatives. And what we've got is we've got different temperatures. We've got cool and heat. Oh, and we've got play. Okay, let's hit play. So we've got a medium temperature there. They're all going around, and see how they're kind of sticking together a little bit. Let's slow it down. And look, there's also showing the hydrogen bonds. So these molecules are wiggling about, jiggling about, moving, and you can see when they get close to another one, there's these grey lines popping out between positives and negatives, or partial positives and negatives. These are the dipole-dipole attractions between them that are keeping together. And because they're really, really strong dipole-dipole attractions, they label them hydrogen bonding. But notice where these grey lines are, they're between molecules, okay? The actual covalent bond between the positive and negative doesn't move or change. It's just these grey lines come into existence when they're closer and closer. These are the hydrogen bondings. Terrible name. Okay? It's the strong dipole-dipole attraction. Okay? Let's see, when we heat it up, they're just going faster, aren't they? Okay? We know that just from our general particle theory and temperature. And then cooling it down, we're slowing down those molecules. See how they're sticking together a bit more? Oh, it's almost as if they're a gas right up here. Yeah? We've got steam happening, water steam. Yeah, all those molecules, there's a big distance between them. They're all jumping, bouncing around the place. That's our model of a gas. As we cool it down, they're clumping together a bit more. Those intermolecular forces, the hydrogen bonding, dipole-dipole, is keeping them together a bit more. We're condensing this gas until we reach a point where they all clump together. Oh, there's a couple of hidden bits out there. But we're getting towards a liquid. Notice they're kind of still falling around each other a bit. Oh, we can't cool it down until we get a rigid structure like a solid. Well, it's getting there though. But you can see we can actually have a phase change there. Look at our little wiggling. Okay, let's heat it up a bit more. It's eating a lot of time, but you can skip ahead if you're bored. It's a really cool simulation. Alright, but we probably should move on. Okay, back to our slides. Okay, 4 videos there on dipole-dipole attraction with some examples there. Good old Bozeman and Tyler DeWitt. Organic Chemistry Tutor 2. Tyler DeWitt, hydrogen bonding common mistakes. Yeah? Even he goes on about the common mistakes of the word hydrogen bonding in the name. Okay. Here's a couple more. Oh, I've already started my animation. I'll go back. Oh, it's not. Anyway, ion-induced dipole forces. Okay. So this is a little bit of a depth study. Let me just go back a bit to the start one. Sorry, guys. Okay. So this is a little bit more in depth, but it will help you. Oh, pause. Oh, that's okay. It will help you understand a later force which we have to learn about, okay? Ion-induced dipole forces exist between ions and non-polar molecules. So you need an ion and you need a non-polar molecule. Okay, when an ion, let's go back. Okay, we've got an ion on the left and a non-polar molecule on the right. When an ion approaches it, it will cause the electrons in the non-polar molecule to move, producing a polar molecule from a non-polar molecule. So here I've got a cation, a positive charge, that's going to move near this non-polar molecule. And it's going to, because it's positive, it's going to drag the electrons over to the side with the positive. And so the side further away from the positive is going to be the partial positive in there. Okay, ion-induced dipoles can be thought of a short-term ion dipole force. It only exists temporarily. It's sometimes known as a temporary dipole, okay? It's forcing a non-polar molecule to be polar for a very short time when they're near each other. It's a very, very weak dipole-dipole force, okay? It's a very, very weak force. But so the ion is inducing or making the non-polar molecule to be polar. Let's look at that animation again. So they get closer. The electrons, the blue, move closer to the positive, and the partial positive is on the opposite side. They get closer and closer. That partial charge gets stronger and stronger, and when they move away, they reduce back again. Smaller and smaller partial charges until they're far enough away that you can call it a non-polar molecule. Okay, that's what happens when you have a cation. I've done exactly the same thing with an anion. Okay, this one will repel the electrons to the opposite side of this non-polar molecule to make it polar. So the partial positive is closer to the permanent negative, and the partial negative is on the opposite side. And now they're moving away, and it's going back to its non-polar state. Okay. Okay, and we also have another one. All right, what we're doing here is before we had an ion inducing a non-polar molecule to become polar, what can also happen is you can have a polar molecule interacting with a non-polar molecule, and when it gets close, it's enough to make the non-polar into a polar. A lot of words here, okay? So on the left, we've got a permanent polar molecule, okay? It's partial negatives facing this non-polar molecule on the right. And when they get close, the electrons in the non-polar are going to be pushed away. And they're going to be pushed away because the partial negative is closer. Let's see what happens in my animation. I think I need to go back. All right, let's see what happens. See, it's forcing this non-polar molecule to become polar as it gets closer. Pushing those electrons to the other side. So there's kind of like a very short-term dipole-dipole interaction for them. A temporary dipole-dipole. So it's weaker than a normal dipole-dipole because it only lasts a little amount of time when they're really close. So we've got a polar molecule making a non-polar molecule into a polar molecule when it comes close. It's called dipole-induced dipole forces. The dipole is inducing a dipole force on a non-polar molecule. Okay. The idea of going through those two, even though they're not in the textbook, is it's going to help you with this last one. And this last one is called dispersion forces. And now, these are the weakest attractions between atoms and particles. Okay? They exist between any molecule, whether it's polar or non-polar, and is very small, and it arises from a very small temporary dipole formed when two molecules are close together. Okay, so they're the weakest, as I just said, and it's the last intermolecular force to be discovered because it's so weak. Okay, so the example that we're going to use is we're going to apply it to two non-polar molecules. Okay. And we're going to look at it that way. That is it when dispersion forces are by themselves, when there's no other attraction but just dispersion forces. But then we need to also consider that it still happens to polar molecules and stuff. But when it's happening to polar molecules, it's also happening in a dipole-dipole attractions. It's so much smaller that it's negligible. Okay, so in our diagram below, we've kind of got a diagram of what's happening. We've got atom A and atom B coming close to each other. Okay, when they're far away, their electrons are really randomized. Okay, when they're coming closer together, though, the positive nucleus also attracts the negative electrons on the opposite particle, the opposite atom, and so you start to get a very slight polarization. Okay, when they're close together, you get attractions from the opposite one there. Okay. They induce a very, very small dipole in each other because the positive protons are attracting the opposite's electrons also. And so they kind of move around, and there's a very slight attraction between the partial positive and partial negative that only exists for a short time when they're close to each other. Okay, I've done an animation on the next slide. Let's see how I did. Okay. So we've got two separated nonpolar molecules at a distance. They have very little attraction. so there's this very small attraction between the nuclei of one molecule and the electrons in the opposite, okay? And so they're going to move a bit closer. Notice my attractive, my dotted line in here has gotten a bit bigger. It's a bit stronger, okay? So as the two molecules, the attractive forces between the nonpolar molecules of the opposite becomes stronger and the electrons shift, okay? So they're attracted to each. So notice how the delta negatives are on the inside. It's because they're wanting you to get close to the opposite's positive as well. We now have two very slightly polar molecules. Sometimes we call them temporary dipoles, okay? Only for a short period of time. But we've also got a repulsion here. The partial charges are also repelling. So when they move closer, look what happens. It gets stronger, this attraction, but it's still very weak in comparison with all the others. But because of that negative to negative repulsion, they start to spin. And when they become closer, they start to line up, those partial temporary polar molecules. And then they slide past each other. Okay. There's that attractive force. And then they start moving away. It gets weaker and weaker. And that poles become smaller and smaller until they're far enough a distance apart where they're considered non-polar molecules again. So it's a very, very short, when they're close to each other, uneven distribution of electrons. A very, very, very small dipole-dipole attraction that's very temporary. So it's the weakest force between the two. Want me to go through it again quickly? They come in. Electrons are unevenly distributed, but they self-align, so they're opposites, and then they move away. That force, that very small force, becomes even smaller and smaller until they're back to nonpolar molecules again. Okay? So the strength of these dispersion forces can vary greatly, but it's always very small, but it can still vary a bit. The strength of dispersion forces is influenced by two things. Molecule size and the distance between the two. Okay, on this first slide, we're going to look at an example of the molecule size. So if we have, on the left, I've got two long molecules close to each other. Okay, and notice that these temporary dipoles, or these dispersion forces, all line up. And because it's a longer molecule, there's more of these forces. There's more little delta positives and negatives along there. So there's like 4 of these in my model. But if we have a short molecule, we only have a smaller amount of dispersion forces. Like on the right hand side, I've only got my 1 there. So there's only one kind of dispersion force unit in there. So the longer the molecule, the more temporary dipoles, the stronger the dispersion force between them. Here, I've given some actual examples. The same text. Okay, on the right hand side, we've got 2 atoms of neon. Okay, neon, there's no attractive intermolecular forces, or there's no intramolecular attraction between neon and neon. They're noble gases. There's no dipole-dipole attraction. There's no ion dipole. They're not polar. There's only dispersion forces. So when they come close to each other, the neon, their electrons will distribute unevenly. And you'll get this temporary dipole attraction between them. But it's only very weak, and it's only very small because they're singular atoms. When we have longer molecules, though, like we've got a carbon and hydrogen molecule here, let's count the carbons in each one. 1, 2, 3, 4, 5, 6, 7. You'll come to this next year, but that's heptane. We've got 2 molecules of heptane. They're nonpolar molecules because carbon-carbon bonds are nonpolar and carbon-hydrogen bonds are nonpolar. So each heptane molecule is not a dipole. So I've only got dispersion forces attracting between these 2 molecules. But because they're so long, we can get lots of delta positives and delta negatives. So because they're longer, there'd be no more dispersion forces between these 2 molecules. So the dispersion forces between 2 molecules of heptane are much stronger than the dispersion forces between 2 atoms of neon. Okay, the dispersion forces between 2 straight chain molecules is much stronger than the dispersion forces between 2 branch molecules. as the straight molecules can move closer to each other. So we're talking about the distance away, okay? The straighter the molecule, the greater dispersion forces between them. Look on the left. They're straight chain. We call them straight chain, even though there's a slight zigzag. They're as straight as that they can be. They can move fairly close together. There's a lot of, because they're closer together, the dispersion forces are stronger. Now look on the right hand side, we've got a branch molecule here. Notice that the branches are getting in the way. They're forcing most of the molecules to be far away from each other. The dispersion forces are weaker. Notice how I've still got 4 of them there, but they're smaller, they're further distance away, they're a lot weaker. So straight chain molecules have greater dispersion forces than branch molecules. All right, another one of these little interactions. Okay, we are looking at the attractive forces between various sizes and shape molecules. So look, small molecules, fairly easy pulled apart. Look at that. Okay, large straight molecules, okay, more force, but still fairly weak. Remember, contrast this to the dipole-dipole attraction. They're coming away a lot easier, but still, the longer particle took more force than the small. Okay, we've got a large straight and a large bent one there, less than the 2 straight ones, and large straight and circular one. All right, a little bit more, because a little bit line up. And let's look at a curved and a circular. We've got not much distance between these. They're a lot closer. A lot more force needed to be pulled away there because they lined up really well. So it's about how these molecules line up and how close they can get to each other. The closer they can get, the stronger the dispersion forces. Okay. There's 2 videos there about dispersion forces. One from Bozeman, one from Organic Tutor. They should help you out. And what I might do is a couple more slides and we'll call it quits there. So it might be a longer video, but that's okay. Found a good place to stop in a few slides. So this is a little bit extra here. A little bit of history to help you put it in context and a little bit of different names that you may come across. So I added this main slide in here because sometimes there's different names for these forces and I don't want you to be confused. And then I got sidetracked. But anyway, sometimes you might hear the term van der Waals force or van der Waals force if someone's really German. Probably pronouncing that terribly still. Okay, van der Waals force is usually just a general name for all intermolecular forces. Sometimes it's just used for those, but it's just a general name for intermolecular forces. Let's keep it at that. Okay, they're named after this guy on the right, Mr. What's his first name? Oh, Johann van der Waal. He worked in the late 1800s and looked at the structures of liquids and solids at different temperatures. So he was one of the first scientists to consider these intermolecular forces. Gives you a little bit of context. He was really early on, so van der Waals is used in a broad term for all of them. Okay. Sometimes these dispersion forces are commonly known as London dispersion forces, and they're not named after the city, but the German physicist Fritz London, and his work built on van der Waals stuff, but he was in the early 1900s, and he built on the ideas that came about that we studied early in the chapter about Heisenberg, Pauli, and Schrödinger when they came along with quantum mechanics and redefined what an electron is. So he applied their new electrons to intermolecular forces, and especially that weakest one, the dispersion forces. So it's often called London dispersion forces. And I saw this great photo come up. I think it was on Wikipedia actually. And so there's Fritz London down the bottom right of this photo. That's from a conference in 1928. It's a conference in Germany named after Bunsen, the chemist, who's also the burner's named after, and it's called the Bunsen Tagung or something very German. annual meeting anyway. So this is a lovely photo from the 1928 one, and there's Fritz London down the bottom right, and there's also this guy that I've circled in green there. I'm going to pronounce it probably wrong. I've never heard anyone pronounce it actually, but I'm going to call it Peter Debye. I'm probably saying that wrong. So he investigated the temporary polarizability, all those induced forces. Okay, so he sometimes is thought of as the father of ion-induced dipole forces and dipole-induced dipole forces, and they're sometimes called, because of that, the Debye forces. Okay, I found it interesting that they were both. Of course, they probably knew each other. Everyone knew each other in science back then. But there they are in this lovely photo. And then I was looking at the other names, and I went off on a tangent. So here's a quick tangent. Shouldn't take too long. Just humour me. You can fast forward the video. Also in this photo, the guy on the top right, Frederick Hund, is also a really cool guy. He built upon Schrodinger's work on how and why electrons are arranged as what they are. And so his name you'll come across in further study is, you hear about Hund's rule, and it's all about how electrons fill orbitals and stuff like that. So there's another superstar in orange, and we've also got Walther Kossel in purple there in the middle. He was a superstar with intramolecular bonding, so his work came earlier on ionic and covalent bonding in the late 1800s. Also did some spectroscopy work and stuff like that. So another really cool chemist there. And the guy in blue, a little bit of more of a tangent, but Casimir, he was one of the early element discoverers of the radioactive elements. So this is right after radioactivity got discovered, or about 20 years after. The first kind of those radioactive elements. So he discovered protactinium, co-discovered it. So yeah, I just thought that was a really, really cool group of people, and it would have been interesting to be at this Bunsen Tagung. And so I put paparazzi underneath. Anyway, there's my rant. Okay, I put in this handy table, and I'm going to start the next slide on the next video on this one. Okay, all about identifying from a pair of particles what intermolecular forces exist between them. Okay, thanks for listening, especially to my rants. Now I need to turn this off. There we go.